Alright guys, so for the next chapter in AP Physics 1, we will be studying electricity. And before we get into the circuits, which will make up most of this chapter, we're going to talk about the basics of electricity, called electrostatics, so charges that, they're not circuits, they're stationary, they're not moving in space, and this thing in this law called Coulomb's law. So the electrostatics part, you guys kind of know already, at least I hope you guys know, because most of us have heard about just by going through our lives. The fundamental law of electrostatics is that opposite charges attract and like charges repel. Okay, so I think everyone knows that. I'm not going to spend much more time on it. And then what I did want to talk about a little bit is how we've defined positive and negative charge. And really, it comes from historical experiments that were done. And what these historical experiments did is they use different materials and they kind of rub them together. So one of the plastic materials is a rubber rod. Okay, so we had a rubber rod, and then we had this piece of wool, and so there's our wool, our fur, and so we would rub the rubber rod with the wool. Okay, and what we noticed is that when we then took that and touched it to a pair of conductive spheres, they would swing. So we would take the rubber rod, we would touch it to the sphere, and then these spheres would repel each other. Okay, and this is where the whole like charges repel idea comes from. And then what we could do, and we found that there's other materials, like maybe a piece of glass. Okay, so this is a glass rod. And then we could take maybe a piece of silk or something. Okay, so this is silk. And we could rub the silk on it. And when we touch that, okay, what we found is that one of them, okay, would be attracted to the glass rod that we rubbed the silk against. Okay, and so the idea is that the glass rod must have a different type of charge than what was on the sphere that the rubber rod, from the rubber rod touching it. Okay, so these are conductive spheres. Okay, and so there's the attractive force. So this idea that like charges repel, like charges repel, opposite charges attract. So there must have been a different type of charge, and we can only find two charges. So what we decided, I think Ben Franklin actually decided this, is that whatever charge this creates, the wool and the rubber rod, I'm going to call that a negative charge. Okay, and whatever charge this created, on the glass rod, we'll call that a positive charge. And so this was kind of an arbitrary thing. He could have reversed this, right? He probably could have called it like black and white if he wanted to. But positive and negative, is simple, it's universal, it doesn't depend on the language you use. And so so that's kind of and this is how we've still defined it. And this is why, even before we found out about electrons and protons and these, the particles that carry charge, we were assigned to them. Okay, it wasn't until later that we found the particles that actually, had these charges. So anyway, so that's how we found these charges. And then we found there's different types of materials. So we have these things called insulators. And on insulator, charge does not flow through it. So those would be things like rubbers and plastics and glass and stuff, right? And then there were these other things called conductors. Okay, and conductors, the charge did flow through. Okay, so these are our metals. And so we had these different signs of charge. We had these different types of materials. Not sure why that just disappeared on us. Sorry about that. We had these different types of materials. But, what we didn't know is how to actually calculate the forces. How many newtons of force existed between these charges. And so, there's this whole historical thing about how to find this. And what we found was this law. It's called Coulomb's law, named after the guy who, kind of found it. And what Coulomb's law says is that the electrical force is equal to some constant, K, times the product of the charges, and so these Q, these are charges, divided by the distance between the charges squared. So r is the distance between the charges. Now, just as an aside here, charges, how do we measure charge? What we do is these have units of coulombs. Okay, so coulombs. All right, and so we would say that something has a certain number of coulombs of charge, and actually a coulomb's a huge, huge amount of charge. So to give you an idea, the fundamental charge, the smallest packet of charge we have is the charge on the electron. Okay, so that's going to be the electron. So the charge on the electron, that has a charge of 1.60 times 10 to the minus 19th coulombs. Okay, so it takes a lot of electrons to make 1 coulomb of charge. 1 coulomb of charge is a huge amount of charge. Okay, so a lot of times what we're going to be doing is we're going to be expressing things in terms of microcoulombs or millicoulombs or picocoulombs. Okay, so know your metric prefixes. Anyway, so the product of the charges divided by the distance between them squared is, the force proportional. So as we have more charge, we have more force, right? And if we have longer distance, this is an inverse square law, so we double the distance, then we will reduce the force between the charges by a factor of 4. And then there's this constant. This is why this was named after Coulomb. Okay, so we have this right here. My goodness. Sorry guys, let me get back to this here. Okay. So we have this constant here, and this has a value of 8.99 times 10 to the 9th, and the units have to work out. So this will be Newton meter squared divided by Coulomb squared. So this is Coulomb's constant. Okay, 8.99 times 10 to the 9th. And this whole equation should look very familiar to you because it's got a similar form to this equation, which we've seen already. Fg is equal to big G m1 m2 over r squared. And so we had this equation when we looked at gravity, and this is also an inverse square law. Okay, so if we cut the distance by 3 to reduce the distance, we'll increase the force by 9 between two masses, right? The same thing with charges. And this constant, 6.67 times 10 to the minus 11 Newton meter squared divided by kilogram squared. So look at these two, man. The electric force is so much stronger than the gravitational force. Okay, we think of gravity as being the strong force, but the reason why gravity seems so strong to us is that we have this huge mass, right, causing this gravitational field. Our masses are ginormous, whereas even a little bit of charge is enough to overcome the gravitational force. When your socks stick to your sweater or hoodie or whatever when you get them out of the dryer in the winter, okay, just that little bit of charge on the hoodie and the socks is enough to overcome the whole gravitational force of the earth as you're lifting that sock up out of the laundry basket or whatever. Okay, so we're going to work with Coulomb's law. We're going to look at this inverse square nature of it. We're going to look at how the charge affects it in class. And so if you guys have any questions, please let me know.